Section 3.2 is addition and subtraction of whole numbers, and we started this last time, and we looked specifically at addition, and we kind of left off on defining what we meant by the phrase less than. Okay, that's where we left off. Not only did we have a phrase less than given to us, like a definition for it, it was this one. We created a definition ourselves. This one involved addition, where we added the sort of missing value to the smaller value, and we created an equivalent one where we subtracted a value from the larger value. Okay, so if you were gone last time, you can pick that up later. We're going to sort of shift gears for just a little bit, and then we're going to move into subtraction. So the shifting gears part we're going to look at is we're going to look at properties. So these are properties specifically for whole number addition. These properties do not work for subtraction necessarily, or multiplication or division. They're specifically for addition. The first property you have is called the closure property. This is one that confuses people. So we're going to fill in the details for it, and then I'm going to give you sort of a word picture of how you can think about it. If A and B are whole numbers, then A plus B is a whole number. Okay, so let me say first of all that this doesn't work for, say, subtraction, right? When I add 4 plus 3, I'm automatically going to get a whole number, in this case 7. But subtraction doesn't work that way. When I subtract 4 minus 3, I get a whole number, but when I subtract 3 minus 4, I don't. So this idea of being able to for sure start with whole numbers and end with whole numbers just flat out doesn't work for every operation. Not only that, but it doesn't work for every number set. Let's say, for instance, that we were looking at even odd numbers. We'll use odd numbers as a better example. If I did an odd number plus an odd number, okay, so not just whole numbers, but odd numbers, what happens when I add two odd numbers together? Do I get an odd number? No, I don't. So there's two things at play here that make this closure idea work. Number one, it's because it's addition. And number two, it's because it's whole numbers and not some other numbering group. Okay? So here's the idea of closure. Closure is the idea that you take a number group and you put them in a room like we're in. So imagine that we had floating around in this room all of the whole numbers, okay? And we pluck two of them out of the air, and maybe it's the same two and two. That would be okay, all right? We pluck two twos out of the air. But we pluck two numbers out of the air, same numbers or different numbers, and we combine them with a specific operation. In this case, we're talking about addition. The question is going to be whether when we combine them with that operation, we get another number that is in this room. All right, so if our room is all the whole numbers, do I get another whole number? Or do I have to go out in the hallway to find something different that I call, some other kind of numbering? So that would not work, right, with the odd numbers, right? If I had all the odd numbers floating around in the room and I'd take two odd numbers and add them together, I don't get an odd number. I get something else, and it's outside my room because only the odd numbers are inside the room. Okay, so that's what closure is. Closure is the idea of taking two numbers and combining them with an operation and still having that same kind of number. And we'll explore more of that when you get to your group work. Commutative is the idea of being able to do the numbers in any order. So when I take 4 plus 3, it's the same as doing 3 plus 4. Okay? Addition is commutative. In fact, kids learn this very early on because what they will often do these days is when you're learning your addition facts, you don't learn all the ones and then all the twos and all the threes. Can't remember which one of my kids it was, but one of them was bringing home flashcards from school. They would bring home these families of numbers. So it would be, like 1 plus 2, 1 plus 1, and 2 plus 2. And then what they would do is they would add on the plus 3s. They would add on 3 plus 1 and 1 plus 3 at the same time. Right? So they didn't just learn all the plus 1s, they learned them sort of differently, where they were adding them together in this commutative fashion as they were learning their addition properties. All right, another one is the associative property. In order to talk about the associative property, you have to have three items. So they've got A, B, and C in this definition. And the idea with this is that we could add them in a different order. So instead of adding A plus B and then C, we could add B plus C and then A. And again, that doesn't work with every operation or with every number set. This is unique to addition and whole numbers. Okay? But you guys know that, because if you were adding numbers together, sometimes it's easier to add the 8 and the 2 and then add the 6, right? Because 8 and 2 make 10. So you try to group things in such a way that the addition's easier on yourself, right? And we do that. That's actually one of our strategies of addition that we're going to learn in, I think it's in 3.4. We're going to talk about this idea of making tens instead of necessarily going in order to add things up. The identity property. There's a unique whole number, 0. That 0, you can write next to it, is called the identity element, okay, or the additive identity element. So put the word element in there to remind yourself. Such that for any whole number a plus 0 is equal to 0 plus a is equal to a. And in order for it to be the identity, it has to work in any order. So it can't just be a plus 0 equals a. And you might think, well, what does it matter? Because it's the same thing either way. Well, it is for addition, but it wouldn't be for subtraction, right? A minus 0, good to go. It's a. 0 minus a doesn't work, right? So the identity property has to work in either order. The 0 or whatever your identity element is would have to go either at the beginning or at the end, or, I mean, like it have to work in either location. All right, what we're going to do next is I'm going to give you, I think you have 4 of them. Yeah, there's 4 of them. And what I'd like for you to do is I'd like for you to write down next to it which identity, or not identity, which property you're seeing used in those 4 examples. Once you've done that, you're all sitting nearby your group members. Compare that you have the same thing your group members have. And if you differ on one, talk it out and decide which of them it's most likely to be. Okay? Which of those 4 properties do you have in these 4 cases in it? I'll tell you right now that it's not necessarily one for each of the 4. Usually I do that, but this one apparently I didn't, so. All right, so at least 2 of our groups are kind of looking at each other at this point. That's good. Looking is good.
And then on the third one, I also associative and I didn't talk. And I got associative. Well, I only thought that is because, I mean, the accusative, obviously, there's something back and forth. Well, I guess I'm right there.
Okay, so some of you are bringing up good points in your groups. I can overhear a little bit of what's going on, and some of you are not agreeing with your group members, and that's totally okay too. So let's talk about these four and see what you got, and if we have differing opinions, we can talk about which one's really happening there, even if one maybe looks like it might be. So what did you guys get on part A? Commutative, I agree. So this is the commutative property. The whole point of the commutative property is that we can change the order moving from left to right. If you think about fixing, a left to right movement of addition or subtraction or whatever you were doing, you can switch the order of that. What's going on part B? That's the identity. The number 0 is shown on the left. It's not shown on the right because adding 0 to something doesn't actually change the value, right? Okay. C is the one where I heard some discussion. So there's two possible things that I had heard. Pretty sure I heard some people thinking that it's associative and some thinking that it's commutative. Okay? So there are 3 elements and there are parentheses, which definitely leads us to think associative looks like a viable choice, right? Because I have 3 items there and there's parentheses associating things together. Association has to do with the way we use the word. We don't always use the words in mathematics the way we use them in our everyday language, but this is one where we actually do. To associate means to group yourself with, right? So if I'm going to associate with Sally, it means that we're going to have some kind of a group organization, right? Maybe we are in a club together, or maybe we just are having a conversation together. We're in a group together, something that we're associated together, okay? The same thing's true in mathematics. Association means that the grouping of them is the same or is different. Something's changing with that. So let's talk about that on C. Do the numbers within the parentheses, those are our grouping symbols, do they change? No. The order changes, but the actual values within the parentheses don't actually change, right? Okay, so that's what makes this not associative. The associative property actually changes the grouping, that is the values that are in the parentheses. Here it's A plus B, and here the grouping is actually different. It's B plus C. So on our example, the one that sort of feels like it almost would be, the values are the exact same, aren't they? But, like you mentioned, Shelby mentioned, the order of them switched. But when the order of something switches, that's actually the commutative property. Okay? It's the commutative property on C. It's the order of them that switched, but what was actually inside the parentheses didn't. So compare that to part D. What happens on D? Yeah, the ones that are actually in the parentheses are different. Here it's 5 and 3. While over here it's 3 and 2. But notice what didn't change. If you move from left to right and ignore the parentheses, it's 5, 3, 2, 5, 3, 2, right? The order from left to right stayed the same. So it's not commutative because the order from left to right did not switch. But it is associative because the groupings of them switched. Okay? All right, good job. All right, I mentioned this just a minute ago. We will talk more about this in, I think it's 3.4, but we're going to address it for the first time here. These are some basic addition and subtraction properties, or strategies, not properties, but strategies. So some of these you've probably used before. Others of them you might look at that and go, why would anybody even teach it that way? And that's okay. You can think that. But you may be one of those why would anybody teach it someday kind of people and teach it that way because the resources that your classroom is using indicate you should. Or maybe current research indicates that kids learn it better or something in that way. So there are a couple of them here we're going to start with. The first one is the counting on strategy. This is one that I remember using all the way through schooling. Maybe some of you do too. You start with one value and then you count up, that should say an additional, not and, or an additional amount of the other value. So, for example, if you had 5 plus 3, you would start with 5 and you would count up the 3 additional values. 5, 6, 7, 8. That's counting on or counting up. Okay? So have you used that before? Yeah? Some of you have. Okay. So this is a pretty common strategy. You start with one value and simply count on or count up from that strategy. Doubles is something you see used more now. I never learned this when I was a child, but my kids have learned this in school. If a student knows doubles, for example, if they know that 3 plus 3 is 6 and 4 plus 4 is 8 and 5 plus 5 is 10, then the idea is to think about numbers that are almost doubles, like 3 plus 4, and to think about them as 3 plus 3 and then plus 1. Okay? So this is a strategy that's totally being taught in schools. I've seen it come home with both of my children as they've gone through elementary school recently. So if you're working in elementary schools right now, volunteering, observing, you're likely to see this strategy being used, being taught. Okay? Doesn't mean you have to think that it's useful. This is true for all of them, not just this one. But it is currently being taught, so it's something that you should be familiar with when you get to a classroom. Okay? So in other words, you think of it as being one more than double the 3. There is some value to thinking about doubles because it lends itself very well into multiplication by 2, obviously, right? If I know all my doubles, then I know my times 2's immediately. Agreed? Right? That's something that's obviously useful as you're thinking further down their strategies for multiplication. Making 10, I mentioned this one earlier. So a method for adding the value of 10, then including the leftovers. For example, this one actually does things where it breaks things apart. So for example, if you knew all of the values that make 10, you knew that 4 plus 6 make 10, and 8 plus 2 make 10, and 7 plus 3 make 10, and so forth. And you had the value 8 plus 6 given to you, then the idea would be to take the 8 plus 6 and break it apart. You start with 8 and you add what it takes to get to 10, 8 plus 2. And then you recognize that 6 is 4 more than that, right? You originally had 6 and you broke it down into 2, so it was 2 plus 4, and that breaks apart into the 10 and then the 4 that's left over for 14. Okay? And I'm showing you this in very simplified examples, like with single digits, but obviously these cases could be made for double digits as well, right? So if you knew that 40 plus 60 was 100, then it might be useful to take the numbers 42 and 68 and break them apart so that you had the 40 and the 60, and then you had the leftovers after that. You'll see that used even more, I think, than the single digit part, and we'll encounter that again. So making 10. The next two are actually subtraction strategies. So counting back, so it's kind of like counting on. So you start with a higher value and you count back to the lower value. So let's say that you had, and again, I'm using simple single digits because it's easy for us to do it in our heads really quickly. So let's say you had 14 minus 3, and you did 14, 13, 12, 11. I counted back 3, and I ended at 11, so 11 is my answer. And it's probably a strategy you've used before. Maybe you didn't have to count back very far, so you just did it maybe even on your hands like I showed you in the air up here, throwing my hands around, right? That's the counting back strategy. There's also the counting on strategy for subtraction. So counting on works like this. You start with the lower value and you count up to the higher value. So again, I gave you the example 14 minus 11. So if you started with 11 and you went 11, 12, 13, 14, I took off 3, right? So I counted from the lower value up to the higher value. That often works very nicely when the numbers are close together, right? 14 and 11 are very close together. The question is simply how far would I have to go from 11 to get to 13? What's missing? So counting on with subtraction would work like that. All right, so let's actually talk about subtraction since I've given you a couple of basic strategies for it. Subtraction is defined in terms of addition. For any whole numbers A and B, such that A is greater than or equal to B, if I take A and I subtract B, it will be a unique whole number C, such that B plus C is equal to A. And all of that sounds really wordy. It's really not as bad as it sounds. If I put numbers in, you're going to be like, yeah, that's what I mean when I talk about subtraction. So let's do some numbers. Let's say I had 5. Okay, I need not a highlighter. Let me try something else. And dots. All right, that'll work. So if I have 5 minus 2, the reason that 5 minus 2 equals 3 is because 2 plus 3 is equal to 5. And you've probably heard them referred to as being in the same fact family. That's something you hear used a lot in mathematics right now, fact families. So sometimes when kids learn addition facts, they learn the addition and the subtraction at the same time even now. That's a very common approach to addition and subtraction currently, one of the current trends. And so the subtraction is defined this way. Or sometimes you'll see them learning all their addition facts first, and then they learn the subtraction facts based on their addition facts. And it looks something like this. What is 5 minus 2? Well, what plus 2 equals 5? 3. So you rephrase it in terms of addition. So it looks something like this. What plus 2 equals 5? Right? This idea of there's this missing piece, and what would it be? I already know my flashcard that says 2 plus 3 equals 5. So if I can remember that flashcard, I can sort of fill in the blank. Okay? So what we're going to do next is we're going to talk about 4 basic, I think it's 4, maybe it's 3. Nope, it's 4 basic strategies for subtraction. And I'm going to give you examples in them, and then you're going to do them and give an example for yourself in your group. So that's why I had you get with your group members. So let me show you 4 different models for subtraction. This one's the most common one. In fact, many kids will define subtraction as takeaway. In fact, if I asked many of you, you might have defined it that way too. What is subtraction? It's takeaway. So here's an example. Abby had 24 rocks. Eli sneaked into her room and took 5 of her rocks. And sneaked is the right verb there, by the way. I know it sounds funny because we don't use it properly all the time, but it is right. He sneaked into her room and he took 5 of her rocks. How many rocks does Abby have now? So obviously we can draw the picture, and we will here in a minute. But the idea behind the different models here is how the word problem, the language, is being used. Takeaway is I have something and I take something away from it. That's what the takeaway model is. I have it and something is removed. In this case it's stolen, right? It's stolen objects. So we can talk about a visual picture for this. So we can draw 24 rocks. My rocks are going to look a lot like circles because they're easy for me to draw on my screen. Your rocks can look like whatever you want them to look like. Not only that, but I have the advantage of being able to copy and paste. Isn't that a nice advantage right now? Sure is. So now I have 12 rocks, 18 rocks, and here's my 24 rocks. So I physically already have these, in this case, rocks. And the idea of takeaway is that I'm removing a portion of them. So I have 24, and I'm going to remove how many according to this word problem? 5. 1, 2, 3, 4, and 5. And the question then is how many remain when I've removed that number? And the answer would be 19. And of course, anytime we're dealing with actual physical objects or language, we're going to identify a unit when we're done, in this case 19 rocks. Okay? I had 24 and I've removed some. It'll depend on how the question's worded. If it asks you to draw it, you will. In this case, there's nothing here. I'm just showing you a way of doing a concrete model. What's important to take away, notice my play on words there, to take away from this is that you have it and you're removing it. Notice how that's different from the next one. Lilise needs to collect 10 leaves for a school project. She doesn't have them yet. That's what she needs, right? That's different. She and Temeskin go out and find 8 leaves. So what do they actually have? They actually have 8 objects, right? And I'm going to draw the 8 objects they have, and the extent to which mine look like leaves is they're going to look like green ovals, because that's what I decided. So your leaves can look like whatever you want, but I'm going to have 8 of them. All right, here are my 8 leaves that I have. But how many do I need? 10. So the question asks us something different, right? I don't have 10 and take 8 away. That's not what's going on. I need 10 and I only have 8. So how many more leaves does Lilise need? She needs 2 more. And I'm going to draw them by drawing in the 2 that are missing as dotted. And I hope that comes through clearly on the screen so when you're looking. Those last 2 are dotted, okay? Because they're not really there. But they're how many more I would need in order to have 10 total, right? They're the missing ones. So the answer, of course, is that I need 2 leaves. But this is a very different question than the last question. Now, part of your mind is telling you, no, it's not. It's the same thing. And, of course, that's the part of you that understands mathematics at a deeper level than the first grader that you're going to be teaching, right? For a first grader, this is a very different question. So if you were working with a child and you could identify that every time they didn't understand subtraction, it's because it was this type of problem, then you've made progress. All right? That's what we're thinking about here, is we're thinking about the type of problem that the child is not being able to solve, or maybe making a mistake on every single time they try it. Okay, so this is missing add-ins. All right, the next one, also a very different kind of problem. Madeline and Monique play basketball. Madeline scored 12 points and Monique scored 8 points. How many more points did Madeline score than Monique? I don't have something and I'm removing it. I don't have something and I'm trying to extend it to be equal to something else, right? I'm comparing two people's numbers of points. It's a comparison model. If you wanted to draw a visual for this particular comparison model, what you might do is you might actually draw tally marks. It would work pretty well for this one. I've got Madeline. How many did she have? 12? And just for the sake of making it easy to count, I'll make my 5s in a crosshatch. So here's Madeline with her 12. And then we have Monique with 8. So she has the same 5 initially, and then 3 more. And if I'm comparing then, what I might do is I might change colors, or I might again use the dotted lines. I'll do both just for the sake of having done it, so hopefully it looks clear. I'm missing this one and this one. That's 2 of them, and then 2 more here. Those are the pieces I'm missing. And I'm not really missing them, but they're the comparison of what's not there. So I can draw them in as to say, oh, look, there's 4 more that I could have had as comparing to the other one. They're equal, right? Of course, no matter how you're thinking about this, the answer is the same. How many does Madeline how many more points does Madeline have than Monique? What's the answer? It's 4. And again, if you could identify, it's 4 points. If you could identify that every time the child misunderstood subtraction, it's because they didn't realize that a comparison model is subtraction, then you'd actually be able to help them in a way that made sense. Because telling them over and over again, it's just 12 minus 8, is probably not going to help them very much. If they don't look at that and understand this is subtraction, that's where the problem is. It's in the language, it's in the structure of the question, not necessarily in the mathematics behind what's going on. All right, our last example is really not anything different than the first 3, but it does present itself in a very different way. This is a number line or a measurement model. The first 3 models are all about sets, right? 1 is 1 is 1. 1 rock is 1 rock. Doesn't matter if the rock's small or big. 1 leaf is 1 leaf, small or big. 1 point is equal to 1 point, right? It's shooting baskets or whatever we were shooting or what we're doing. In this example, it's not the same because it's miles. And distance is different. Akeem drives 15 miles to the mall. As he's on his way home, his mom calls to ask him where he is. He states that he's coming home and he's driven 8 miles so far. How far is Akeem from home? So Akeem is actually driving lengths, right? It's not really whole number objects. We're representing them as whole numbers here. But we recognize that he could drive half a mile, right? He could. So in terms of a model, this is going to be a number line model. He starts at 0, and it says he drives 15 miles to the mall. So here's our mall over here. I don't draw very well. I've told you guys this before. But here's Akeem's house, right? And here's the mall with lots of stores in it. That's right there, my mall. Looks almost like a crown. Sorry. And it's 15 miles apart. And what he's actually done is he's driven, it says, 8 miles home, right? And the question is, am I for miles? 15 miles down here. And the question is, how far further does he have to go, right? This is missing add-ins, but it's missing add-ins for miles, right? For number line lengths, not for physical objects. It's measuring distance. So the answer, of course, is still the same answer as we would have had before, 15 minus 7, which would, 8, 15 minus 8, which would give me 7, right? The answer is 7 miles. But we're thinking in terms of lengths of things, not counting of objects of things, which makes the problem present very differently than the last missing add-ins one, which was about leaves that we had from before. So what we're going to end with today, we have 6 minutes. You're going to take 4 of them. You're going to create 4 word problems. You don't have to solve them. I just want you to create them. Write them down. 1 for each of the 4 models in your group, okay? And then at the very end, each of you will present 1 of your 4 to the class. Okay, if you're not quite done, it's okay, but I'd like for us to go ahead and share them so we can wrap things up for today. So I need a group, maybe who didn't quite finish, to tell us what they got for the first one. What did you do for your example on the first one? What do we have? The takeaway model. All right, what do you have, Melissa?
Abby has 6 flowers, and mine took away 4. How many flowers does that have?
Okay, so she had the flowers, somebody took them away. All right, how about an example for missing add-ins? What do you have, Caitlin?
Victoria has 4 chickens and she needs 6 for her science class. How many more does she need?
All right, so she has some of the chickens, but she needs more for some kind of science experiment. That sounds a little bit freaky, but it will work. It will work. Thank you. How about the third one, comparison? Actually, I'm going to call on Sally's group because I overheard you guys doing your comparison model. What did you guys do for your comparison model?
We said Katie ran 10 laps and Shane ran 6. How many more did Katie run than Shane?
Okay, so running laps, and that could be considered the comparison model, right? Because you're comparing what they did. You also could almost do it in a number line model because it's a half and a half kind of thing. So it depends on how you think about it. It sort of blends between the two, but that's kind of how the number line model often does, is it blends between two things. So that's a good example. And what did you guys have for the last one for your actual number line model?
Susan traveled a total of 6 miles. She ran 3 miles. So then how many miles did she walk?
All right, so we have miles that she ran, miles that she walked, and we're actually filling in the missing piece to add up to a total amount. Good job, guys.